All right, good afternoon, everyone. It's truly a pleasure for me to introduce Rebekah Yang, who's a system engineer at CNA. CNA is a nonprofit research and analysis organization which supports public agencies. Her research interests include digital modernization and emerging technologies for the public sector with emphasis on aviation. Rebekah did her master's and PhD here at University of Illinois, and her bachelor's was at Swarthmore College. In addition to this simple introduction, it's truly a pleasure for me to introduce Rebekah for a couple of reasons. One, she was an amazing student here. And the second is she combined what I would say an important thing for a PhD student, away from her high ethics and high morals. She's very, very intelligent. She finished with 4.0, but above that, she's very, very humble. And that's what makes her distinguished. I get to know her as a student, as a colleague, and I cannot be more proud. Rebekah, the floor is yours.
Yeah, thank you so much, Professor, for that introduction. It's very kind. And for inviting me here today. I'm really excited to be here. And it's great to see a lot of new faces, a couple of older faces too. Yeah, I got to see some of the new buildings on campus, and I'm looking forward to the lab tour later. But yeah, it's great to be back and to see so many of you here. So as Professor mentioned, I work at CNA now, and I'll talk a little bit about the company, but I'd like to focus on some of the work that we do with the FAA around emerging technologies. So that's what I'll talk about today, and kind of give an overview of some of the work we've done and some of the state of where things are with a few different technologies. So a little bit about CNA. Again, it's a not-for-profit research and analysis group. We've been around for about 75 years, since World War II, and are dedicated to the safety and security of the nation, whatever that means in our research and analysis. We're a federally funded research and development center, mostly with the Department of the Navy, but we do work with civil agencies as well, which is what I do. And you can see on the map here a snapshot of some of the different federal, state, local partners that we work with in agriculture, emergency management, human and health services, law enforcement, aviation, a lot of different areas. And particularly for today, we've spent about 25 years supporting the FAA, mostly around air traffic systems and information systems, and trying to help the FAA modernize and look forward to new emerging technologies like what I'll talk about. So some quick background about the Federal Aviation Administration. So they're responsible for the safety of the National Airspace, or the NAS. And that's just, it's a very complex system. And it's a network of different airspaces, facilities like control towers, command centers, airports, and all of the infrastructure that's required to move our aircraft from origin to destination. So their main function is to perform air traffic management. That's all of the functions related to moving aircraft from one airport to another airport. So it's a very complicated, complex system with a lot of safety and critical implications. So for the FAA, when they're considering new technologies that might be integrated into the national airspace, there's a lot of potential challenges. So I'll talk about two specific technologies today. The first is uncrewed aircraft systems, or UAS, and the second is artificial intelligence and machine learning. So in our work, we look at things mostly from a regulatory perspective, so it might be a little different than what we do in academia here. But hopefully be interesting and give you kind of a different perspective on some of these new technologies, and specifically the challenges that have to be addressed before we can fully national airspace. All right, so I'll start with uncrewed aircraft systems, or drones, colloquially. So I realized I didn't put a great mix of pictures here, but we are talking about the smaller drones that maybe some of you have flown or seen, or someone's getting a license in it. Earlier today, Amazon is looking into delivering packages with these kind of drones. We also have in the future air taxis that will carry people, as well as fixed wing drones, maybe for longer distance surveying, So a lot of different applications, even in the construction industry, lots of potential for surveying infrastructure, for doing pavement inspections, and a lot of potential applications that we see. So the industry is really driving a lot of this innovation, and the FAA, they're getting pushed by industry to look at how they can make sure that these technologies are integrated into the NAS safety. So right now, a lot of the rules and regulations for UAS are based on the type of operator that is operating the drone. So you have recreational operators, so people who are hobbyists, and they have kind of certain regulations they follow. You have commercial operators who need to be certified if they're flying on behalf of someone or a different entity. And then you have public safety and government, which have their own special authorizations and kind of waivers to do different tactical things that they need to. So just a snapshot of drones by the numbers. So I took this from earlier in November, and the FAA has a website where you're supposed to be registering your drones. And you can see there's almost 1 million drones that have been registered in the US as of yet. About 330,000 of them are commercial drones, and more than 500,000 are recreational drones. So just by the sheer number, as compared to traditional aircraft, like the planes that we all fly on or cargo, there's many more drones that are out there, and there will be many more. So the FAA knows that it can't use the current system of manned air traffic management to manage UAS. Right now, the current system is air traffic controllers communicating one by one with all the pilots, right? But there's no way that they would be able to do that with the millions of drones out there. So currently, the FAA is working on UAS traffic management, or UTM. It's actually been an ongoing effort, maybe about 2 decades worth of research and policymaking. And it's a collaboration between NASA, the FAA, and other agencies, as well as industry. So they're looking at defining a system where they can manage UAS operations for low altitudes, that's under 400 feet, so under where commercial airplanes have been flying, that is separate but complementary to the existing traffic management process. So the interesting thing about this is it's going to be community-based and cooperative. So instead of the FAA kind of centrally controlling and certifying everything that's going on, a lot of the onus is going to go to the community and to the actual operators themselves. So the FAA will be specifying the rules and regulations of what UTM looks like, but the operators are going to have to coordinate and manage, negotiate, and be responsible for their operations. And they'll work with commercial industry UAS service suppliers, or USSs, to help manage their operations. So these service suppliers, they'll develop apps or different softwares that you could subscribe to as an operator. You could use that to submit your flight plans, to negotiate with other operators on if there's a conflict, or to get information about restrictions, about weather conditions, things like that. So the FAA is really trying to put a lot of the infrastructure and the support for UAS onto the industry, because they know they can't manage everything themselves. So this is just a snapshot. It's from about a year ago, just to show visually the FAA here and the commercial service providers as an intermediary, talking to all the different drones. You can see many different types of operations that are going on, but this is one of the ways that this is from NASA, that they envision what UTM will look like in the future. All right, so moving on to a couple of challenges with UAS integration. As with any new technology that comes into the FAA's consideration, they have to balance safety and innovation. And it's a really big conflict that they have to deal with all the time, because they're responsible for the safety of the aircraft and the passengers, but they also want to innovate so they can improve safety and efficiency. So a lot of FAA systems take decades to modernize, to update, because they need to go through so many strict safety and security processes. Another challenge, as I mentioned, is currently the rules are based on the operator. So there are a lot of waivers that need to be given if people want to do certain types of operations. It's a very manual process. For example, if you want to fly at night or over people, you have to have special waivers for this. Currently, the FAA is trying to actively reduce some of these restrictions with new regulations or automated systems and processes, but there's still a lot of work to be done. A couple key examples that if you do get into this area might pop up. These are some of the hot topics right now that industry and the FAA are discussing. The first is beyond visual line of sight, or BVLOS. And this is the ability to fly a drone further than you can see, which right now you have to be able to see the drone to be able to fly it. So you can imagine if you can fly a drone beyond your visual line of sight, this can open up a lot more operations, like package deliveries further out, serving operations like for railroads, things like that. So that's a big topic right now that's under discussion. You also have remote ID, which is a public safety sort of issue. Last year, the FAA passed a rule that starting in about a year or two, UAS must broadcast their identification and location at all times. So any drone up in the air, this will allow law enforcement to quickly identify it, see if it's in the right place or who owns it, or if it's if there's some kind of suspicious activity, they can figure out what's going on and contact the right person. Some other challenges of flying multiple drones with one person flying multiple drones. That's another big issue right now. And then also fairness, because it is community operated and cooperative based, there is concern that one commercial entity, maybe a very large commercial entity, could sort of take over the airspace or be able to reserve certain parts of the airspace more than others and not allow equity of access. The last challenge that is kind of underlying through all of this is cybersecurity, which I'll focus on for the next couple of slides. CNA has done a lot of work over the last 4 years or so in cybersecurity and some of the special considerations for UAS. So I'll talk about that. We've been developing a UAS cybersecurity framework over the last few years, and we use the NIST cybersecurity framework. That's the National Institute for Standards and Technology. They have a standard or set of guidance for critical infrastructures and how to secure the cyber needs of that. So you can see on the right, there are 5 different components to the framework. The first is to identify the business goals and the assets, the people, and the objectives that you're trying to protect. The second is to actually protect the assets through access control or different safeguards, encryption, things like that. The third is to detect, so detecting threats. How do you do that quickly? The fourth is how to respond to cyber attacks and threats quickly and with the right amount of people. And the fourth is recover. So after a cyber attack occurs, how do you recover your operations, communicate, update your protocols? So we took this framework and applied it to the UAS ecosystem, and we looked specifically at 2 different aspects. The first is federated airspace management, which is the information exchange between the FAA, the USSs, the service providers, and the operators. So all the information that they're having to exchange about their flights. And we also looked at infrastructure. So that's including communications and navigations and the information that's passed from the drone to the operator, those kind of command and control links from the vehicle itself. So we came up with, I think, something like 50 different research areas that we were going to recommend to some agencies to look at, but I'll just highlight 3 of them here that I thought were interesting. So the first research area that we are recommending that that industries and stakeholders in the US community look at is the issue of competing stakeholder objectives. So the US environment is going to support a lot of different types of stakeholders and actors. You can see, we've already talked about federal agencies, as well as local and state governments, law enforcement, academia, international entities, and so forth. And all of them will have different security objectives and requirements and different business goals and missions. So a governing authority, whether that's the regulatory agency or a third-party impartial agency, we recommend that someone needs to define what all of the UAS business priorities are, what the requirements and the standards they need to follow, what trust frameworks they need to use, legal requirements. So they need to specify all this so that the competing stakeholder objectives do not cause vulnerabilities in cybersecurity. The second that I'll highlight are supply chain vulnerabilities. So this is being talked about quite a bit in this area. So with current commercial airlines and manned traffic vehicles, the FAA is responsible for certifying like all of the aircraft, all of the avionics on the aircraft, all the systems that are being used to control and pass the information. But with UAS, we're pushing it more to the industry. So it's a lot of commercial software, our suppliers that are being used, and a lot of cloud services are going to be used as well. So all of these sort of third-party commercial industry products will have supply chains upstream, and those supply chains could introduce risk into the final product. So I think 2 years ago, there was a pretty well-publicized cyber attack by affecting SolarWinds, and that was a supply chain issue where someone really far up the upstream, their software was compromised, and it affected the products, some really important security products kind of at the end user level. So similarly with UAS, we have, it kind of looks like life cycle actually here. We have raw materials suppliers, manufacturers, distributors, everything in the upstream that's contributing to the assets from UAS. And third-party software, third-party updates, cloud storages and services. All of these upstream products need to be also looked at, not just the downstream products. So, and then finally, one last research area that I'll highlight that we emphasize in our recommendations is a zero trust approach. So this is also a very large topic with the US government right now. There's a White House initiative on increasing the use of zero trust for federal agencies. And it's essentially, what it is the legacy kind of approach to cybersecurity is to build a really strong perimeter outside of your the resources you're trying to protect. And essentially you're assuming that anyone who's outside the perimeter is not trusted, but everyone who can somehow get in is trusted. So that's the legacy current approach. And then the zero trust approach assumes that there is no perimeter, that you just don't trust anyone. And anyone who wants to access or interact with your resources has to be individually verified and identified. So kind of making the trust area much more limited in size. That's something that is a kind of a new approach and something that we recommend for the UAS environment, because having the single parameter on the outside is not sufficient. Great. So we also, as I mentioned, looked at infrastructure concerns. I won't really go into this too much detail, but we looked at communications, navigation, surveillance, command and control links of the vehicles itself. And we found that a lot of the typical cybersecurity threats that you can see here are all applicable. Many of them are applicable to these infrastructure resources for UAS. So before I move on to machine learning and artificial intelligence, I just wanted to go through a quick use case on cybersecurity and UAS. So CNA also works with a lot of public safety entities, and they look at their new technologies all the time, including UAS. So there are some law enforcement agencies that are just starting to look at UAS, and some that have already developed full UAS units and resources. But regardless, any UAS system that they use is going to be also vulnerable to cybersecurity attacks. So this is problematic because it could potentially compromise the control of the UAS. And if that happens in the middle of a mission, like a pursuit mission or search and rescue, then it could really enable that mission to fail. So we participated in a NIST challenge with Greece, which is our industry partners. And the challenge essentially wanted us to look at a cybersecurity attack that is relevant for public safety and to come up with a countermeasure for it. So we picked one that was actually pretty straightforward, but something that is very widespread, which is the use of default telemetry settings. So telemetry is the data that comes from the drone to the operator, and it's telling everything about where the drone is, the environment of the drone, and it's what you need to operate the drone. So just like, if you guys remember with Wi-Fi routers, like back in the day, the username and password is always admin or something. And if you didn't change it, then people can very easily hack into it. So a very similar thing where some of these drone technologies just come with default settings and some people don't change them. And the default settings are published. It's very easy to get to. So an attack could be to kind of brute force, go through all the default settings until you find one that works, and then you can essentially take control of the drone. So this is something that we looked at, and we developed a system here that essentially has a lot of different radios on it, different ways to communicate with the drone. And it's a proactive countermeasure to, before you fly, you run through a script that automates all of these default settings to see if you can break into the drone. If you can, it sends the operator an email to tell them, hey, you need to change your settings. So we flew a demo with it and kind of demonstrated the effectiveness of the system, and currently have more funding to sort of try to bring that to commercialization. So that's just an example of how cybersecurity is tangibly noticed in UAS. Right, so I'll move on to talk about artificial intelligence and machine learning and some of the kind of state of where things are with the aviation community, as well as work that CNA is doing to try to address some of the gaps in integration. So in general, as you can imagine, I mean, machine learning has over the last decade experienced a lot of growth and innovation, and there's so many different applications out there for many different industries, including aviation. And there's a lot of potential for it to enhance the safety and the security and the access of the aviation industry. However, there are a lot of challenges to actually improving and using these technologies because of some of the qualities of machine learning, which I'll talk about. So just a quick note, I have the definitions of AI and ML here. Machine learning is a subset of AI, but it's what we focus on because it has kind of the most momentum right now and potential for application, especially in the aviation world. So there, as I mentioned, a lot of different applications for machine learning and artificial intelligence, including in aviation. I'll just point out a couple here, but for example, image recognition. One idea is to take pictures of an aircraft, and you would be able to potentially identify where damage is or damage is likely using different machine learning classification techniques. You could also use it to predict how weather and traffic will affect and delays at airports, and try to get ahead of that and introduce the best types of initiatives that will help reduce delay at airports. And let's see what else. And then also natural language processing. A lot of our communications with pilots and even at the command center between facilities is all verbal. They still talk and give commands. So being able to process some of that language, that natural speech, and analyze it could be very useful. So with all the different types of applications, there are also quite a few challenges because especially the machine learning process differs quite a bit from traditional software development, where you usually have a list of requirements, you write the code, and you can sort of one-to-one match, okay, I met this requirement, we're using this line of code. But with machine learning, you're using a learning process, and you more or less come up with a black box or something that's much more difficult to explain to and kind of link back to the requirements. So a lot of these challenges need to be considered before we can fully integrate these types of technologies into the national airspace or to approve them for use. So in terms of some of the specific challenges, I mentioned the learning techniques. Right now, the current guidance and standards that are used to approve and validate software for aviation doesn't consider learning at all because it's so new. So we don't really have guidance on how to test machine learning technologies for aviation. The validation of requirements is difficult. As I mentioned, with traditional software, you kind of link the requirements directly to the code. But with machine learning, you can't really do that because you don't always know, you can't always take apart the model and explain it fully and connect it back to the requirements. And then the final challenge I have up here is the verification of results. So typically with traditional technology, you come up with a test suite, all possible inputs, and you test them and make sure that you always get the same outcomes. But with non-deterministic and more complex AI technologies, it's a lot more difficult to come up with a good test suite or know that you've tested all of the possible inputs and outputs. So there are a couple ongoing efforts to develop guidance for using AI and ML in aviation, some from international agencies, European Union, and a few from the US. The Food and Drug Administration is doing a lot of work because there's a lot of interest in using machine learning for software medical devices. And then you have NIST, who's looking a lot at the risk in general of AI. And they tend to come out with guidance that a lot of federal agencies will use. So with CNA, we're working alongside with NASA and the FAA on a paper to kind of think of what the first steps of this would be. And we ended up proposing a classification framework. So from a regulatory point of view, just like with UAS, you can't sort of integrate all of UAS into the national airspace. You have to kind of start small with the smaller drones, larger drones, and eventually people carrying drones. You don't sort of go for the full picture all at once. You gradually integrate these technologies. So similarly with AI ML, we wanted to see if there's a way to sort of figure out a roadmap where we could classify different types of AI ML and potentially figure out what the level of rigor or requirements would be to approve them, and which technologies might be potentials for earlier adoption versus later adoption. So while I'm going through this, I'll just mention a use case that I'll come back to at the very end. But an example of an AI ML technology for aviation is an assisted runway identification application. So this could be in the cockpit for a pilot. Maybe they want some additional help looking for identifying where the runway is. So this system would be able to distinguish between a canal or a road or a railroad line and know where the runway is, kind of highlight it for the pilot to help them as they're landing. So in our classification scheme, we're trying to break down different properties of AI ML technologies. And we came up with functional as well as technical characteristics. So functional characteristics talk about what the AI is actually helping with, what type of activities and actions. And we came up with 4 different types of functional types of functions. So the first level is planning. So maybe this technology is helping you plan or giving you advice for what is coming in terms of traffic. It could also be a decision-making tool. So it could be strategic planning, or it could be tactical, kind of a shorter term tool to help with decision-making. It could also be some kind of a perception function where you're detecting an event or the possibility of an event happening. And then finally, you have management control, which is actually making decisions about a certain situation that's happening. And it could be either the system is giving information to another system, or it's providing recommendations for actions to a human. The other side of characteristics we have are technical characteristics. So this refers to the aspects and the complexity of the technology itself. So the functional criticality refers to mostly to safety, if it has the ability to affect or improve or reduce safety hazards, or to contribute to safety hazards. Temporal criticality is the amount of time that an end user would have to process or validate the information. So that will affect kind of the criticality of the system. We also have model accuracy, which refers to how well the model represents the actual physical thing that you're trying to model. Whether it is, so for example, a neural net may not be able to physically represent the model as well because it's assigning weights, right, in a network. And then finally, we have trustworthiness of AI. So that refers to the ethics of the technology, as well as the security, safety, and the robustness of the technology. So those are the characteristics. I mean, if we kind of put them on at the same page together, we get a better picture of what the framework looks like. So you have the technical characteristics in the orange, and then the functional in the blue. And you can see on the top, we have the first arrow here represents technical criticality. So a lower functional criticality and a higher, and then a lower temporal criticality and a higher. And then we have this black pyramid here that represents the amount of level of design, verification, validation, testing, and oversight that would be needed for this technology. So at the top, you have a lower level of rigor or design needed, and that's if the technology is more trustworthy, more accurate, versus you would need a higher level of rigor and design and validation for systems that are higher criticality, are less trustworthy, less accurate, need more requirements to make sure that they are doing what they're supposed to be doing and acting in a way that they should be. Similarly, we have the functional characteristics, so juxtaposed against the level of rigor. And you have the planning functions sort of at the top. They may not require as much rigor to approve. And then you have at the bottom the control and management functions like autonomy that would require a lot more rigor to be able to approve, because they're giving a lot more actions and decisions. All right, and then applying the classification scheme. So in our paper, we talked about these two different types of characteristics, and we propose that they both need to be considered. So some of the other organizations that we've looked at will only consider one or the other. They might just consider functional criticality and just look at the level of autonomy of AI and use that to decide how much testing needs to go into it. Or they might just look at the risk. But for a regulatory agency, it's important to look at both and to kind of balance the two. And by looking at them together, we have a different perspective here in this graphic. We can determine the level of rigor that's needed. So if you have increasing functional risk, increasing technical risk, that's going to lead to an increased amount of rigor or requirements that's needed to approve it. So just as an example, going back to the assistive runway identification case study that I mentioned, we could notionally, this is not a real project or product at this point, we could assign it a medium functional risk because it's a perception type of function. It's identifying, detecting runways. So that's kind of a medium level of risk. And then we can also say that it has a potentially higher technical risk because the criticality, so the time where the pilot sees the results of the technology, they don't have as much time to react, right? So it's a short time frame to decide if that is really a runway or not, and that's where I'm going to land. And it could potentially is giving an incorrect result, could result in potentially misleading information that affects the safety of the operations and the ability for the pilot to correctly identify the runway. So for this particular use case, we could place it maybe around that area, and you can see that it's sort of towards the higher end of level of rigor, or the amount of testing that would be needed to approve this type of technology. All right, so I think I'm kind of getting to the end of time here, and just to say a couple final remarks. So I talked about two different types of emerging technologies that are relevant to the national airspace. And these are big topics for the FAA as well as NASA and a lot of the stakeholders in the aviation community. And those are UAS as well as AI/ML technologies. And we've talked about the different challenges and some of the gaps that are needed to fully integrate these technologies into the airspace safely. And to do that, we need to look specifically, I highlighted some of the cybersecurity concerns that need to be looked at and addressed before we can do integration, as well as the need to update regulatory frameworks and processes to address some of the gaps in how we can regulate these types of technologies. So there's definitely a lot of additional research that is currently being done. We're doing a lot of work at CNA, and there's also many other companies and agencies that are sponsoring this work as well. All right, so I think that's the end of my talks. I I just want to acknowledge the papers that I reference, some of them have authors as well from the FAA and NASA, CNA, and there are a lot of other key contributors to this work. So thanks so much for your attention. I think we may have some time for questions.
Questions? Questions? Angelique.
Thank you. Thank you, Rebecca. It's great to see you as well, and great presentation and great work. On slide 25, forgive me if I didn't quite understand it. I was kind of unsure why the functionality and the functional criticality, temporal criticality, accuracy, and trustworthy were opposing. So I think the top is the low levels for the criticalities of functionality and temporal, but the accuracy is high. And then oppositely, when the functional criticality is low, then the accuracy of the model is less. I didn't quite understand why, what that means.
Yeah, so this is sort of a matrix, right? So yeah, typically they should actually be considered independently a bit, but basically this is saying a technology that has a lower criticality either temporally or functionally would likely have a lower level of rigor. And similarly, if the model is more accurate, like easier to explain, and also one that is more trustworthy would also have a lower level of effort because people feel more confident with it. But if it's less trustworthy, like there's a lot of ethical risks to it or potential security issues, then you would need a higher level of testing and rigor to be able to like approve the technology. Does that kind of
Yeah,
answer?
it does.
Okay.
Yeah.
Right. Thanks. Thank you.
Right.
Cool. Thank you for the nice presentation. I have two questions. So before UAS, I think the terminology was UAV, and all of a sudden, at least for me, it became UAS. So I was wondering why that is, why the change of terminology.
Yeah, no, that's a great question. So UAV is uncrewed or unmanned aircraft vehicle, so it refers to the actual drone itself. But UAS is the system, so that actually refers to the vehicle and the ground control system. So it's sort of the whole package. So
Okay.
it's.
And the other question is, you mentioned that like for commercial aircraft, the FAA kind of releases everything and they create their own like devices to monitor everything. But whereas with UASs, they're pushing towards the industry, creating their own technology to be integrated into the system. And I was wondering whether the additional cost of creating these technologies from the industry side, plus the additional complication of operating the UASs, would present a hindrance to their proliferation in the future.
Sure. No, that's a great question, and I think it's definitely more. Yeah, there's a much more of a burden on the industry, but they see so much potential. Like if once there's so many applications like package delivery and surveying and inspection. So I think they see that it's worth it because there's so much market opportunity. Like yes, they'll need to, and there's. I talked about remote ID. There was actually a lot of pushback from industry because it meant they would have to retrofit some of their vehicles. And I think there's like 50,000 comments on the public proposal for that. So yeah, so there is definitely pushback and there's negotiation between industry and FAA and different committees. But I think they understand that there's so much potential and it's worth it to invest. But yeah.
So if this takes off and I buy my own drone, then someone in the whoever releases this is going to know that this is my drone and it's flying right here. And it's going to tell me like 8 land that you can't fly there.
For remote ID.
That's at some point, yeah.
So yeah, so that's the idea is so that law enforcement, because right now there's no way to track who's flying which drone. So for law enforcement, that's an issue for them. If there's a drone that's doing something illegal, like they need to be able to track it. So yes, in the future, you're supposed to be broadcasting your ID, like a VIN number. Essentially, it's like a license plate. They can look it up. Yeah.
That's Professor Yang. He's working on now the congestion
Oh yeah.
of the drones. I don't know, did you have the chance to talk to him?
I did. Yeah.
Yes,
He doesn't like it.
that's some research he's doing because they're going to be so many. So the congestions that you have on the highway, you're going to see it in the sky too. All right.
Yeah, I was wondering what could be an example of the zero trust approach. Like, how do you decide what to trust and what not?
Yeah. So well, essentially, you don't trust anything. So each resource is responsible for its own either its own protocols or there's a if it's part of the larger ecosystem, there's a protocol that is already in place. So an example of that for UAS is each drone, as well as each USS operator, every single communication that they have with each other needs to be trusted. So they don't sort of automatically trust it because you're on the same network or something. Every time you send a message, you need to send your like an encrypted code or certificate with it. Yeah, so that's something that they're looking at doing some pilot programs on.
Yeah, thank you.
Thank you, Rebecca, for the nice presentation. I actually have a question about the using artificial intelligence for detecting the runway. How is that going to be used, and why is it considered on the functional side of the higher risk? Because I think it will be an assist to the pilot actually. And also one more question: have you worked on like actually quantifying the risk of the accuracy or like misclassifying the runway?
Mm-hmm. Yeah, so I guess first off, with this use case, it's just a notional, like kind of a made up use case just to illustrate the use of the framework. So it's not something we're working on or that we know other people are working on, but just as an illustrative purpose. Yeah, so in terms of the higher technical risk, it is also depending on how the pilot will use it. If it's just like kind of on the side that they may or may not glance at, then maybe it's not going to be that high of a risk. But in this case, if they're using it to assist in landing, then if it does give misleading information, then it could have really severe safety problems or confuse the pilot or something. So that's why it's in the higher risk category. And there's not a lot of time for them to like really look at the picture and like see, compare. It's urgent. So. And then the second question is, no, we haven't looked into quantifying the risk. Yeah, that's a whole nother thing, and I'm sure very complicated, a lot of research that needs to be done.
I have just the robotics question.
Okay.
So since you have some like those technologies, they are like kind of black box, so they have those kind of risks. But because you also mentioned they have been trying to be applied in the aviation. So like do they have something to like to regulate this kind of errors to prevent some like safety issues during operation?
Yeah, so right now, the use of AI in general is not really allowed because there's no way to certify it right now. We don't have, the FAA doesn't have guidance on it yet. Yeah, so that's something that they'll need to come up with how to mitigate some of those risks. So that's some of the research we're looking into a bit, and then other groups are definitely looking into, but there's no kind of set guidance on it yet. So yeah.
So thank you for the great presentation. My question is to general one. Like, how do you think the insurance policies are evolving with like emerging technologies?
Insurance policy, interesting. Yeah, that's a good question. I mean, I've never really thought about it. I do know, like, for example, the challenge that we were part of, like, they required all the companies to have insurance. And I think if you're a drone company, you probably have your own special insurance, because even if it is a small drone, like the rotors, especially for the quadcopters, the rotors are rotating very quickly and you could injure someone if it fell out of the sky, things like that. That's why there are regulations where at this point, you're not supposed to fly above people or at night or beyond where you can see the drone. So yeah, but that's a good question. I haven't really looked into the insurance, but I imagine that's a whole field of itself.
Any other questions? Yes.
So at the beginning, you mentioned that the framework is community-based and cooperative. I guess just a general question, who becomes the governing entity, right? At the end of the day, as you mentioned, if there are negotiations or conflicts, who gets to decide or who gets to steer? Will there be like steering committee between the community, or at the end of the day, do those questions get brought up to the FAA and FAA becomes the final say? Because someone has to champion it at the end of the day, even if it's a community-based framework.
Yeah, no, that's a great point, and that's something that the FAA is still trying to figure out. If it becomes a safety issue, then it's likely the FAA, or if the FAA will still be sort of somewhat involved if the drone like enters into controlled airspace, which is what the FAA is responsible for like near an airport, then the FAA needs to be notified because it's a security issue. In terms of like conflicts and things, especially around fairness, for example, that's something, yeah, we're not really sure if it's the industry is going to somehow take care of that, or if there's going to be a third party that will help negotiate. But yeah, it's still not very clear, some of those areas.
That's great. Thanks. Any other questions?
Professor, we have a question on Zoom.
Yeah, please. That's fine. Okay, Laura will. You can go
Just
ahead
leave
and
it.
ask it, Laura.
Oh, yeah. So Professor Yang is saying, thank you, Rebecca, very nice presentation. I know FAA has been contemplating on regulating the allocation and use of low altitude aerial space for a few years. Just curious if you can share a little bit more about where FAA is currently in this process for freight versus for passengers.
For
Freight
versus
passengers.
Yeah, I mean, I think in terms of right now where they are, I mean, UTM is still, it hasn't been realized yet. There's still pilot programs and research that's going on. In terms of freight, I have heard that that is something they're looking into. I'm not sure if they've started to develop concepts for it. Usually what happens is, and you can find the concepts, they're publicly available, but the FAA will kind of commission someone to submit a concept, and then NASA actually does a lot of the research, and then it goes up to the FAA. So I haven't heard anything about like large freight, large cargo operations. But I know for the people carrying operations, there are already some initial concepts that have been developed that are available online. So that's something that NASA is doing research on, and you can see some of the research publicly available.